Welcome everyone. In this video, we will solve a problem from USAMO 2005, problem number 5. So this problem talks about n blue points and n red points. Totally you have 2 n points. So you have n blue points and you have n red points. And they are arranged in the plane such that no three are collinear. And they have one interesting condition. So a line in the plane is called a balancing line if it contains one red point, one blue point, and on either side of it, it contains equal number of red and blue points. For example, if there are 3 blue points, then there must be 3 red points. So here on the other side, you will have n-4 blue and n-4 red. If you focus on one side of the line and make both equal, it will automatically render the other side configuration to have equal red and blue points. So we are just going to focus on one side because the balancing line itself contains 2 colors in equal number, one red and one blue. Now they are asking for to prove that there exists 2 balancing lines for any given configuration. So this is in that way more powerful. So it's talking about a general configuration, right? So let's get started. Suppose these are my points on the plane. I'm just going to randomly arrange them. 1, 2, 3, 4, 5, 6, 7. And 7 blue points. 1, 2, 3, 4, 5, 6 and 7. In the last video, we learned about convex hull given a set of points, right, in the plane. We similarly construct convex hull for this configuration, which will be a convex polygon whose vertices are the points on the plane. Alright, case 1. Suppose if some 2 colors lie on the convex hull, like this. You see, this is the convex hull. So just by looking into it, out of some intuition, I built the convex hull. But the argument I am making will be more rigorous, as we have rigorously defined a convex hull definition in the previous video. So if you have not seen that, just go back and watch it and try this question. So convex hull will be a convex polygon whose vertices are these points, the 2 end points that I'm talking about, these 2 end points. Those will be the vertices of this. So if some 2 colors are adjacent, you see, we will directly get 2 balancing lines. So in the circumference of this polygon, you can easily construct the line consisting of those 2 points, and definitely no other point will lie on this line, as the condition is that no 3 points are collinear. And due to the convex nature, all the points would lie on one side of the structure. This is because if the convex set intersects again at some other point, then there will be some gap in the line that we constructed which will lie outside of this convex hull, contradicting the fact that this is a convex set. So at first we should realize that this is a convex set. Convex hull is a convex set. Due to this contradiction, there will be no intersection of this convex set again with this line. Call it as L. Call it as L. Therefore, the entire structure lies on one side of this line L, which imply if there are we know that there are 2 end points, and out of that 2 points already lie here on the line L. So remaining 2n minus 2 points lie on one side, out of which n minus 1 is blue and n minus 1 is red, and we are done. Well, what is the other balancing line? You see, in the perimeter, if you get 1 red and 1 blue, eventually you will get one other color change as you traverse from the blue to the red in the opposite way. So when you witness one color change, you will be guaranteed that even if you have repeated blues, the color shall change to red as it ends with red. So there will be two color changes happening at least. So as depicted, here there is one color change and here there is another color change. Therefore, you will get two balancing lines, say L1 and L2. Next case is when all the colors on the perimeter of the convex hull are same, say red or all blue. So as you could see in this configuration, the convex hull has the vertices from one color, so it is monochromatic in that sense, which is red. All the blue colors lie inside it. So we have to get a line that passes through the convex hull somehow. What we will do is take a ray from one point and that passes through the adjacent vertex on the boundary of the convex hull. And we rotate that ray so that it merges with the adjacent side, passing through the other adjacent vertex of the convex hull. Through this rotation, something magical happens. We shall prove that there will be an encounter of balancing line in this configuration. So taking U as the reference in the node, we have the initial ray. So let's call this ray as IR, initial ray, and this is FR, the final ray. So in the initial ray, you have all the points towards your left, that is 8 blue and 2 reds. I am also considering the red that is incident on this ray. So that amounts to 8 blue and 2 reds. Now as you rotate this incident ray, you will get to the final ray. And with respect to U, now all the points happen to occur on your left side. So it will be 8 blue and 2 red inclusive of this red. So you see, the last point to reach to your right is the red point that is incident on the final ray. So therefore, at each angle of rotation, point by point moves from your left side to right side. This is what is going on. And the last point to reach is 1 red. So you are starting with 8, 2, 8 blue and 2 red. And eventually the points are decreasing. So maybe let's say 1 blue goes to this side. So you get 7, 2 and the last would be 0, 0. But just before that step, it will be 0 blue and 1 red. Because this red, which is incident on the final ray, is the very last one. So 0, 1. So this decreases to 0, 0. And eventually, in this process, 8 minus 2, the difference between blue and red is 6. Over here, the difference is 7 minus 2, which is 5. And over here, the difference is 0 minus 1, which is minus 1. So the discrete values, integer values, go from 6 to minus 1 continuously. Continuously means what? Like step by step, 1 by 1, there is a decrease in 1 or increase in 1 each time. For suppose if red decreases, there is an increase in 1. So 6 to minus 1, there is no jump, but there is a discrete continuity that's happening over here. Observing that, we must encounter 0 at some point of time while we perform this rotation. And that's when the number of blues and number of red on your left side would become equal. I cannot exactly point out at which point because it depends on the configuration, but this is guaranteed. Number of blue and number of red will eventually become equal, and therefore that is the ray we are interested in. Now if you just extrapolate that to a line by extending it to the opposite side, you will get the balancing line. So this is performed just by considering one random vertex. Now convex hull is a polygon, is a convex polygon. So you will have like 3 vertices at least. So just take another vertex and you will get one other balance line and you would be done. So think about this problem in your own way and let us know your ideas in the comments. Just two ideas we incorporated here. One is the convex hull, and the second idea, by working on the perimeter of convex hull and pivoting on a particular vertex. So these two shall easily break down the problem. There is no formulas, no big derivation of any formulas here. It is entirely based on your intuitive imagination. So I hope you enjoyed. Thank you for watching everyone. Bye.